Hello, everybody. My name is Paul Vanderboer, and I'm a Senior Director of Data Science at Prosus. And today I'm going to talk to you a little bit about how at Prosus we've built various AI platform capabilities at global scale. Before I do that, let me tell you a little bit more about Prosus. So Prosus is a global consumer internet group and one of the largest tech investors in the world. Through our investments, we serve more than 1.5 billion people in more than 80 countries. And I'm part of the Prosus AI team that's based out of Amsterdam, although most of the customers, as you can see on the globe here, where these colors indicate transactions or orders or other kinds of interactions, are actually in different parts of the world, such as Eastern Europe, Russia, India, and also various parts of South America. And throughout the group, we actually look at the businesses we invest in 4 different segments. So the first one is classifieds, which are online platforms that allow people to trade secondhand goods. The second one is payments and fintech, which you see various brands here that are basically have products like credit, or we have a big payment gateway as well through PayU. Then we have a third business segment that we call food, basically food delivery companies. And then the fourth one is edtech, educational companies. Not all the brands of the Prosus Group are here, but they give you a bit of a flavor of what we have. And almost all of these businesses are actually consumer facing, which means that some examples here of businesses in each of those segments. For example, in the second column there, you'll see PayU, which is a payment gateway based out of India, and it has an app that allows you to, as a customer, to request a credit. Or you have Brainly, which is a big platform an educational platform that allows students to ask questions and look for answers to those questions, which has over 350 million users by now. So these various businesses really operate at a tremendous scale, and all of them have various swarms of machine learning models built into the product. So on the classified side, these are models that, for example, help understand whether the content that people are uploading onto the platform is harmful or not, or whether the prices that people are trying to charge for these secondhand goods are good for optimal liquidity. On the payments fintech side, it's related to credit, like I mentioned. On the food side, there's all sorts of models running behind the scenes. On the first, let's say when you open the app, what kind of dishes do you see as a user? But also on the background, once orders get placed, predicting how long the cooking time might be, or which rider should bring that food item to you. And on the educational side, a lot of it's related to what sort of courses we should recommend to users, but also specific to the questions that users ask, what's the best answer for the learner? So all of these different models, the swarm of ML models that's at the heart of many of these products, we continuously seek, especially at the scale that we operate, to make it easier and faster to deploy these in a reliable and useful manner. And therefore, that's where the machine learning platform capabilities come in. And the way we think about these capabilities that we build as part of the machine learning platforms is essentially to support various different parts of the machine learning workflow. And the way we've defined this workflow is a 7-step workflow. It's not, very surprising. Many of you will have defined maybe your own workflow with slightly different names, but it's the workflow that all machine learning use cases essentially have to go through to bring models into production. And the way we think about the ML platform is essentially all of the tools and technologies, but also, of course, the practices and processes that help automate, speed up, and support various parts of this workflow, such that the machine learning models can be brought to production and to the users in a faster way. And essentially, when we look at where we want to spend time for accelerating this workflow to help us, get these machine learning models deployed at scale, we actually try to quantify how much time in each of the businesses they spend or we spend on building, putting these, basically training these models and then putting them into production, and all the steps that are required as part of that workflow. And through the exercise of quantifying how much time actually we spend on each of these parts of the workflow, we can then decide where we want to focus on building machine learning platform capabilities. So what I'm going to do now is I'm going to walk you through some of these capabilities that we've built at each of the different businesses and how they look. And I'm going to start with OLX, and I promised I would talk to you about how we've done this at global scale. So I also want to tell you about how this business operates at a global scale. It's basically the world's fastest growing network of trading platforms that operates in more than 30 countries around the world. And the goal of the platform, the product, is to help people sell and buy all these different products like household goods, but also cars, houses, help them find jobs, and much more. And on the platform, there's over 300 million monthly active users. Just to give you a bit of a sense of the scale here, those users upload millions of images, listings each day, just as the one you see here. And each listing comes with a set of images. Like this listing you see here is basically a user that's trying to sell a car, a secondhand car, for a given price. And the car, just like any other items that people can sell here, these are in a way unique items. This is user-generated content, and each listing is unique because it's secondhand goods. So the conditions and the price and the way that the user is selling this is going to be unique, and that actually makes for a quite interesting problem from a machine learning point of view, because we need to understand, or we try to understand as much as we can about this unique listing, such as in the case of a car, what's the brand, the make, the model, and other kinds of categories like electronics. What is the equipment? When was it made? What are the other specs that we might want to be able to retrieve from the listing that maybe the seller hasn't listed, but we can infer from either the image or other things that we know about the product. And all these attributes, this data enrichment exercise and this attribute extraction allows us to then also make it easier to return, for example, the right item to a buyer, right? One that's searching for the items that they're looking for. And so when in OLX's case, when we started to basically go down the route of really scaling some of the machine learning activities, we also had to lean heavily on the data platform that was also being built. And in particular on the OLX side, this is a very mature data platform that has various functionalities that make it possible to basically deploy these machine learning models across the business. And the architecture that you see here is a high-level architecture. Some of the components that were built along this, what I've called earlier, the machine learning workflow, to standardize some of the activities there. And it starts with collecting the data in a systematic way across all these different brands and platforms, and then dumping that data in a data lake, but also making sure that, very crucially, it's also findable and searchable through a data catalog, which isn't just a let's say catalog to search, but also has a set of let's say governance elements around it, like who owns the data source, what are the health metrics related to the data, classification on whether this data is personal or not, etc. And once that data makes it through the data lake, it ends up in reservoirs, which is our name for isolated and dedicated data storage that gives specific access to data for whatever use cases that might exist. And what you can see then is the data processing, especially I'm showing here the use case of machine learning, basically comes in two groups. So one is the real-time consumption, and the other one is anything that's longer than 5 minutes. And one of the important components here in the center is the data hub, which is essentially a data hub that not only makes it possible to, for example, find data, right? So it's the single go-to place for data when any machine learning or data scientist wants to actually access the data. But it's also a place where data science professionals can share the data sets, with other data scientists in the group. And then there's a scheduler, which is Airflow based, which is essentially ETL as a code platform with pretty advanced dependency management, but it also supports templating, step expansion notifications, which can be helpful if you're running data pipelines on a regular basis, and you want to make sure that you get alerted or triggered when something isn't happening as it's supposed to. So this data hub is a crucial part to the setup here that becomes the go-to place for any data scientist. And what happens after, let's say, the data scientist has trained the model and wants to bring this to or integrate into a product. Obviously, there's experimentation piece and testing, which I won't go too deep into, but we call it here Loquisis, which is our self-service tool for performing some of these experiments. But we also downstream have built recently some capabilities on making it easier to serve the predictions. And what's interesting about this part of the architecture, in particular the data API that you see here, is it's built in a very generic and standardized way, such that the end user that's actually consuming the predictions of the model can call this data API in a easy and common way, such that they don't need to worry about what's behind that API. So it sort of abstracts the complexity of the infrastructure from engineers that are consuming the data, for example, as part of the front end or other parts of the product. And the data API, however, is only working on batch predictions, right? So this is for non-real-time use cases. And what we've built for real-time consumption or real-time inference, basically, of machine learning models is a Kubeflow-based service, in particular KF-serve, that allows for real-time inference of any sort of models that are required. In particular, for now, we've looked at doing that for non-image models, but we're also building on expanding that for image-based models. And both of these basically provide a standardized application integration option for any of the use cases of these machine learning models. And through the team, we're also contributors to the KF-serve library. So that's just a little bit on how OLX has built some of these platform capabilities. And I want to take it now to a different business that we have in the Prosus group, which is iFood. And iFood, again, to give you a bit of the context of the scale, it's basically the leading food delivery player in Brazil and is expanding across South America. And like many of these food delivery marketplaces, it's a three-way marketplace. So you have consumers, you have drivers, and then restaurants, or in some cases, grocery outlets. And iFood is only in Brazil fulfilling 40 million orders a month, which is a tremendous number, and that happens through 150,000 delivery partners, about 200,000 restaurants. And some of the ML use cases you can imagine here are related to the front end direct experience of the user. So what sort of dishes should we, as iFood, recommend to the user? That has to do with obviously past orders, but also location of the user. And then once the user orders a dish, how long will it take to deliver, showing the user that estimated time of arrival. There's models running that try and estimate whether we can maybe group orders to optimize sort of the logistics process. So all of these different models that are triggered through a food delivery order, basically lead to millions of real-time synchronized decisions every single day. And it's in this case that a machine learning platform really becomes important. And if we look at what we've done at iFood, basically what I'm showing you here is one of the solutions developed in-house that we've called Bruce. And what Bruce allows data scientists at iFood to do is help train models easily on AWS SageMaker. So basically leveraging a managed service of AWS, creating a wrapper around that to standardize the way that the setup for AWS is for some of the iFood use cases, and also makes it easy to create SageMaker endpoints to serve some of these trained models. And the reason that it was decided to go this route is that actually creating this wrapper allows for standardized best practices, and it avoids data scientists to have to interface directly with the infrastructure, which especially for data scientists that aren't that always have the same level of comfort with some of these software engineering practices, this is a great solution. And so it provides that sort of ease of use, but it's also a central point of collaboration. So anybody can contribute to the Bruce library, and obviously very conveniently also avoids having to go through AWS documentation every time we want to use SageMaker. So that's on the training and deployment side. But there's several other components that are part of the iFood machine learning platform. So one really important one is the feature store, and that's based on Databricks and Spark for the near real-time features, but uses Redis for storing and serving. And it currently contains over 100 features that each are calculated millions of times. As you can imagine, the total number of feature value pairs easily exceeds billions for all the combinations of users and values that exist. Actually, I shouldn't say users, just all the different entities that we care about. So it's going to be eaters, restaurants, and riders. And so the amount of feature data can easily grow to billions of records with millions of actively retrieved actually in during model inference under very low latency constraints. So maybe the last part to mention on the feature store is that this is a unified data flow combining batch and real time. So this is something that we also contributed to the Spark AI Summit recently, and that's the design that you can also look at if you'd be interested. And then for the CI/CD part, trying to implement and really make the MLOps practices part of this workflow, we use Jenkins and Airflow, which uses an internal repo crawler, and all of the models are updated on a daily basis. And as part of that, we also have metadata that's collected that makes it easy, for example, to check in on models and monitor them using a standard dashboard. So then, I want to talk about the last food delivery business here that we're going to talk about today, which is Swiggy, which is similar to iFood in many ways as it does food delivery, but operates in a very different geography. So it's the leading food and on-demand delivery platform in India, and has a remarkable average delivery time of under 32 minutes. So again, you can imagine what that means for some of the models and basically systems having to run in the background that manage the entire delivery process from order to eater. And also Swiggy has thousands of delivery partners across 500 cities in the country, and has over 100,000 partner restaurants. So to give you a bit of a sense of the scale, in 2020, more than 1 biryani was ordered per second. So that's a very serious number of dishes that are going around. And what's also notable, one last thing about the skill that I want to highlight here, is that 80% of the traffic that goes through Swiggy, and this is approximately true for iFood as well, happens during 2, maybe 3 peak moments a day, which is when people eat at lunch and dinner primarily. And again, that brings in quite some complex requirements to some of these machine learning platform capabilities. So Swiggy has built its own homegrown data science platform, and it's been battle tested in a sense. It's been already in production for 3 years. It's been used by dozens of data scientists inside the company, and it's part of a larger platform strategy at Swiggy, including the data platform, which has actually a big advantage because it has the data science platform has native access to features in the data platform, but it's also tightly integrated with the experimentation platform and other parts of the platform that are being built. And we found it to be easily extensible. So, for example, recently added support for TensorFlow, but also PyTorch, and primarily focuses on the last mile of the ML workflow. So I'm going to show you a high-level architecture here, and I'll talk you through sort of the key elements of the stack here. So it's a JVM-based stack. It's a reactive microservice-based architecture for the live scoring, but obviously also handles pre-scored models. And for the training, we primarily use here MLLeap and Spark, and also have support for, as I mentioned, TensorFlow, PyTorch, and also SageMaker. And for the features, both batch and real-time features are handled by this part of the data science platform. It has a pluggable feature store that's uses DynamoDB and Redis, and the features are basically SQL queries, and onboarding them is very easy. It also includes a testing and experimentation capability for shadow testing, A/B testing, and has a pretty flexible runtime that uses EC2 or Kubernetes clusters. And all of these clusters are isolated in a way to avoid failure. And this platform is really built for scale, and because it actually handles some of the highest throughput and lowest latency use cases at Swiggy, so including ads, real-time recommendation, frauds, ETA, etc. It has characteristics, and the architecture is built to be able to handle that, right? So for example, the peak load is over 300,000 queries per second, and to give you a sense, models with approximately 20 real-time features can maintain a P95 latency of about 20 to 25 milliseconds. And so it supports hundreds of real-time and batch models combined, has over 1 billion predictions a day, 1,000 plus features, each of them calculated millions of times per entity, and so has proven to handle, also to be able to handle scalability over time. So with that, I conclude, let's say, the three data science platforms, machine learning platforms that we built, and just wanted to highlight a couple of the elements that each of them have successly been able to put together. But before I end, I want to actually share a couple of general considerations, and having built and having had the experience of building these platforms at scale. One of the things to keep in mind is that when you design these platforms, is to make sure that you design them for change. And what I mean with that is, the design should actually provide its own interface, ideally, such that you can actually remove the tool interface from the user, which actually removes the cost of change. So if you want to add, remove, change parts of the platform, you can do that behind the tools interface, right? And so that brings in the advantage that it's easy to change and sort of move over to new technologies if needed. Another thing that we found successful is to use multiple things in parallel. So not just use one, but try different things, because different tools and technology will serve different purposes. And given all of the things that are available out there, because people are making them available either open source or the new commercial tools, you don't need to reinvent the wheel. Doesn't mean you don't need to be careful to make trade-offs, because obviously a lot of solutions are out there, but not all of them are actually, most of them won't be made for your particular, and in our case also our particular use case. We need to take care of, does it work for our data modalities, for example? Does it work well for text? Does it work well for images? Does it work well with the other interfaces of our architecture? And so making sure that you, even though you don't need to reinvent the wheel, you make a careful trade-off with what you end up going with. And as I said, we're dealing with these use cases that really do require scale, and you need to make sure that that is the case. We found multiple times that, while the solution seems to meet all of the requirements, actually when you start doing, scaling this out, and some of our businesses, have massive growth year on year, you need to make sure that the tools can remain cost effective, but also they can keep meeting the SLAs that you have set. And last but not least, we've in many of the parts I discussed today, really infused MLOps practices, but it's important to keep doing that, right? This is an evolving field. A lot of the tools and practices that we use continue to mature, and by taking those into account in the design of the tooling and the practices that you set up as part of the ML platform, I think you run, say, the bigger chance of meeting the needs that you have set off at the start. And with that, I want to end with a special thanks to the teams in these three businesses: OLX, iFood, and Swiggy. Every time I said "we" in today's presentation, I actually meant they, because they're the men and women that have built these platforms. Thanks to them for having done that. With that, I end today, and I think we have time for Q&A now. Thank you.
All right. Thanks so much, Paul, and welcome for the Q&A session. Uh,
Thanks, Sam.
so, quick reminder to everyone to, if you're not already in the stream panel, jump over to the stream panel and get your questions into the chat uh, chat pane. Paul's been doing a great job already answering questions in that chat pane. So I think we're caught up there. Paul, I wanted to get your take on, with you kind of sitting at the process level um, and having visibility into what these very different businesses are doing. What are some of the observations that come to mind for you and seeing the way these companies have built what looks like very different approaches to ML platform?
Yeah, that's an interesting one. Indeed, I have the advantage that with the team we basically get to see how these each in their own right very big businesses with hundreds of millions of users in very different countries and different parts of the world, actually different business models, are trying to build ML platform capabilities to serve their ML teams. And at the let's say at the highest level, a lot of them seem very similar, right? I mean, like I mentioned, you've got this ML workflow. You start with some data, you need to process that data, you need to train a model, needs to be served under some SLAs, and so forth. And all those components, come up when these different teams build models. However, when you look at some of the business requirements, you also see a couple of very different things that then translate into different technical choices, right, in the architecture. And I spoke about two food delivery businesses, and they're as I mentioned, actually you're talking about the moment from order to delivery. That depending on which business you're talking about can be close to half an hour, right, and or sometimes 3/4 of an hour. That means that in that time period, all these different things need to happen, concurrently, or sometimes serially, one decision following the next, making sure that this can be done within that promise that we have to the consumer. And so in those cases, that translates to certain architectural choices that you have, certain features that you want to have available at certain moments in time. Another thing that happens is also the kinds of data modalities that play an important role. So OLX, the first business I spoke about, those are online listings and things that people try to sell. And so there's a lot of pictures involved in those. And so if you're dealing with image data, all of a sudden that also has different implications for what data you're putting into the model, how your data stores look, the kinds of attributes and things that you're trying to get out of these images using computer vision models, and so those things definitely have let's say implications that then translate to different architectures and solutions in the different businesses. And what also matters, which is actually something I found pretty interesting in looking at the journeys that each of our businesses have taken on this path, is that the moment that you step in, so whether you did this 3 years ago, started 2 years ago, or starting now, actually has pretty big implications for the tools that you actually have available to integrate, right? If you started 3 years ago like Swiggy, then you have to basically build a lot of things yourself. And I think, like Chris mentioned, some of the tools we see today, the rough edges have been taken off, right? They've been smoothened. And so you do have, if you were to start on some of these components today, very different options, solutions, whether commercial or open source, available. That means you can sort of cash in on the technical dividend, especially their open source, right? And all the problems this community has had, you don't need to reinvent the wheel, and you can sort of take them into your solution. So, and you see that because for example, Swiggy started 3 years ago and has a very specific set of choices and tools that they've done. A lot of this home built, as I described, whereas some of the businesses that are starting today are able to use some of the managed services out there that are both scalable and also cost effective.